Hello everyone, I'm Aditya and welcome to ISTE Crypt's machine learning series. Today, we'll be looking at gradient descent. Now disclaimer ahead, this has some math involved in it, but do bear with me. Before we learn about what exactly gradient descent is and how exactly it might be helpful to us, let us look at an example of linear regression again. In this graph, the blue dots represent data, and the red line is the slope that will help predict values of x or y when given either one of them. The idea is for the red line to be as close as possible to all the data provided to us, in this case the blue dots. Suppose the x-axis represented the weight of a person and the y-axis represented the height of a person. Our red line will help predict what the height of a person might be when given the weight of a person. Now this is all well and good if we are able to get this red line. But how and where exactly will you place this red line, right? This is where gradient descent comes into play. Gradient descent is an optimization algorithm. In our case, it is what will help get this red line as close to all of the data in our data set, so that we're able to make a prediction as accurately as possible. To understand how exactly gradient descent works, we have to first define something called as the loss function. Now, as you can see, the actual height value is greater than the value predicted by our red line. Let us define a loss function here, which is the square of the difference between the predicted value and the actual value. Sum this over all the data points in our dataset, and this will give us our required loss function. The red line can be written in the form of the equation y is equal to mx plus b, where in our case, y would take the value of height, x will be the weight, slope and intercept become parameters that help to predict our value. Now, if we plot the loss function with respect to the intercept and then with respect to the slope, we get a graph that looks something like this. Now keep in mind, by intuition, the loss is essentially how off your predicted value is from the actual value. So our goal must be to minimize this loss function, and hence we need to somehow determine the values of our parameters such that this loss will be minimized. A painstaking method to determine this point is to keep plugging in different values of the x-axis and determine when exactly the loss is minimum. And hence, this is where we'll be using gradient descent. If you take the derivative of the function with respect to the parameters represented by the x-axis, either the intercept or the slope, you will notice that the slope tends to be steeper away from the minimum point than when it is closer to the minimum point of our loss function. We can now use the formula here to update the values of our parameters. The formula being that the new value of our intercept will be equal to the old value of our intercept minus the learning rate times the slope. Now, what exactly is this learning rate? So, learning rate is a configurable hyperparameter used in the training of neural networks. Learning rate controls how quickly the model is adapted to the problem. Now, if you have a small learning rate, you will take forever to reach the minima. And if you have a large learning rate, you will skip the minima. So when you update the intercept with the formula, you notice that when the slope is steeper, you update the intercept or the slope value to a much greater extent than when you're actually closer to the minimum value and your slope is less steep, and you will notice that you end up taking baby steps towards the actual optimum value. Gradient descent would stop when the slope value gets as close as possible to 0, which in this case is towards the minimum point. Now there are three types of gradient descent. The first one is batch gradient descent. Now this is the first basic type of gradient descent, in which we use the complete data set available to us to compute the gradient of the cost function. The second type of gradient descent is stochastic gradient descent. Now, stochastic gradient descent updates the parameters for each training example one by one. Depending on the problem, this can make stochastic gradient descent faster than batch gradient descent. One advantage is the frequent updates allow us to have a pretty detailed rate of improvement. On the contrary, the frequent updates are more computationally expensive than the batch gradient descent approach. The third is the mini batch gradient descent. Now, mini batch gradient descent is the go-to method since it's a combination of the concepts of stochastic gradient descent and the batch gradient descent. It simply splits the training dataset into small batches and performs an update for each of those batches. This creates a balance between the robustness of stochastic gradient descent and the efficiency of batch gradient descent. Now, we move on to another important topic called backpropagation. So, when you do a forward pass, or you get to know how accurate your prediction is. Now, after that, you need to do backpropagation to update the parameters to help predict the output more accurately in the future. Now, for the purpose of understanding the next few slides, we'll have y is equal to mx plus c in the format of z is equal to wx plus b. Now, in a forward pass, you pass through the neural network from your input side and then you make a prediction at the output end. Once you make the prediction, you will apply the loss function to see how accurate you are at this step. Then you need to backtrack and update the parameter values, or in fact tweak them so that next time you're able to make a more accurate prediction. This backtracking is what we call backpropagation. Backpropagation essentially calculates gradients at every step of the way. Without dwelling too much into the math, all you need to know at this point is that from a particular layer, the partial derivative of the cost or the loss function with respect to the weights of that particular layer is equal to the partial derivative of the layer's output prior to activation times the activation from previous layer. Now, I know what I said might have been a little confusing, but looking at the formula will give you a better understanding. Here, C is the cost or the loss function. A of L minus 1 is the activation from the previous layer. Z of L is essentially the W times X plus B of your present layer. And W of L is the weights of your present layer. This is done for calculating the intercept parameter as well, the formula being slightly different. Now, this process is done iteratively for all the layers till we reach the initial input layer and update the parameters W and B, which was initially chosen as random numbers. To get a better understanding of what exactly forward propagation is, do check out ISTE Crypt's deep learning playlist. Now, this brings us to the end of this video. Continue on to the next video in our playlist to know more about machine learning.